Okay, guys, just to let you know, I am going to be recording this and I will post it. All right, so question 1 is explain why the function f is continuous. So this goes all the way back to chapter number 1. So the first thing for number 1 that you need to do is you need to find the limit as x goes to pi of f of x. So you need to find the limit on the left and the limit on the right, and it turns out that the limit is pi squared plus 3. So that's like part A, if you will. Then part B is you need to find f of pi, which turns out to be pi squared plus 3. And then part C, we now can see that the limit as x goes to pi f of x is equal to f of pi. So this is why it is continuous. So that goes all the way back to our definition of continuity in chapter 1. There are 3 parts to it. Hopefully you remember that. I'm kind of reviewing a little bit for the final exam. By the way, I should mention that there's actually a shorter way to do this same problem with one step. And if anyone can tell me what that shorter way is, and I mean completely distinct from what I've done here, please let me know in the chat. It could be worth a virtual gold brick to you. Question number 2, to evaluate this limit, we got to do the limit as x goes to pi. Now we've got to plug in f of x, which is x squared plus 3, minus f of pi. Well, we saw that f of pi was pi squared plus 3. All of that divided by x minus pi. And then we can work out this limit, and you will get an answer of 2 pi. The answer for number 2 is 2 pi. And then, of course, my third question here is what the heck is question number 2 represent? Well, it turns out that question number 2 is the definition of the derivative at pi, which is 2 pi. So this is the definition of the derivative. That should be an E. Okay, so there's your warm-up again, just some stuff review from chapter 1 and chapter 2. So before we go ahead and start looking at today's section, which is on 3.6, I want to go over 2 important announcements. And those of you that are here with me, I think you'll appreciate hearing these. Number 1, next Monday, you will have your next and final test besides the final exam. And it will be on Monday, not Thursday. It is Monday. I've pretty much consistently made most of my exams on Thursday. This one's going to be on Monday, and the reason I'm making it on Monday is the week after that is the final exam. So I want to make sure we've got a little bit of time to review for the final exam. So we're going to have this test next Monday. Please note that we are only going to cover sections 3.1, 3.2, 3.3, and 3.4 on this exam. So it's basically the exact same content that we had on our quiz a couple of weeks ago, with the addition of Rolle's theorem and MVT. In other words, what I'm telling you is 3.5 and 3.6 will not be on this test. So the stuff we did last week and the stuff we're doing right now will not be on the test. Please make sure you're following the protocol, which is to log in via your Chromebook, keep your monitor or your camera on and your microphone muted. And then you also might want to take some time to restart or clean out your Chromebook. I've had some students that said they can't read things or it's acting weird. You need to try to take good care of that Chromebook before the exam. Nothing worse than being in the middle of an exam and then having things go south. The second announcement is I made an announcement. This is actually an announcement in Canvas. So if you already have read my Canvas announcement that I posted, then you can disregard what I'm saying because you already know what I'm going to say. And by the way, if you have all of your work is up to date, you've done all of your tests and quizzes, all of your homework has been done, you can ignore what I'm going to say. But you need to read the announcement that I posted in Canvas, and I will give you an important date. This date, Friday, December 3rd, not this Friday, the next Friday, 9 p.m., that is the last moment you are allowed to turn in any missing work, quizzes, tests, etc. The week of the final exam, I will not accept any late work. So please hear me now and read it again and make sure you get that part taken care of. All right, so let's go ahead and get into section 3.6. Again, I hope you've already watched the video that I posted, so now I'm going to kind of re-dip your brain in some of this calculus. Example 1, it says greatest concentration is the name of this example. The concentration of a drug in the bloodstream T hours after injection into muscle tissue is given by, and here's the equation. C is probably for concentration and T is for time. And we want to know, when is the concentration the greatest? So we want to find the greatest amount of concentration. So what we're basically going to do here is we're going to use what we've learned in section 3.3, which is the first derivative test. In fact, that's what I'm going to use for most of these examples. And we've got our function here. So the very first thing I'm going to do, actually, before I do anything, let me mention the domain. The domain for this function is just going to be t greater than or equal to 0. What I'm telling you is the concentration of this drug in the bloodstream, the t value, as long as it's greater than 0, it makes sense. We're not going to deal with negative t value. We're not going to somehow magically have a concentration before we actually put it into the bloodstream. So this is our domain. Okay, so let's go ahead and find F or C prime. C prime, I'm going to kind of pretend that I've done this, but I'm going to cheat a little bit just to speed up this process. In order to find this derivative, I'm going to have to use the quotient rule, but I'm going to just pretend that I've already worked it out in advance to speed the process up here a little bit. The denominator should look pretty familiar, as you would expect, since it's low d high minus high d low over low low. So there's that low low squared. The numerator, though, there was definitely some things that needed to be multiplied together and factored, etc. Obviously, it looks like we have a perfect square. So this is the derivative of the function c. Now, what I want to do with that is I want to set that equal to 0, and I want to figure out when it's equal to 0, and that's going to give us what we call the critical numbers. Now, the critical numbers here, I'm not referring to this. In fact, maybe I should write critical numbers. I'll just write out critical number here. The critical numbers, well, it looks like it's going to be t equals, let's see here, 4 and -4. Now, I claim that -4 cannot be a critical number, though. And guess why it cannot be a critical number? It can't be a critical number because we just said that the domain had to be all values greater than or equal to 0. In other words, none of the values for where t is less than 0 makes sense. So now what I'm going to do is I'm going to do my graph here. This is C prime. And the only critical number we have on that graph turns out to be 4. This number here, that's t. And it turns out if I pick a number less than 4 but bigger than 0, let's say, let's say 2. So if I pick 2, this is positive, 4 minus 2 is positive, and that's positive, and everything's positive, so this is positive. If I pick a number bigger than 4, like let's say 6, positive, negative, positive, so that will be negative. In other words, our function f is going to, or our function c is going to be increasing here. This is c, and it's going to be decreasing over here. So that makes t equal 4 the relative max. The relative max, and that's what we're looking for. In other words, at 4 hours, we will hit max concentration. And that's the answer to our problem. Okay, so this is my first example of an optimization problem. So what I was trying to basically optimize here was the concentration of a drug in blood. And it turns out that at 4 hours, it will meet its max concentration. If you want to know what that maximum concentration is, you would just take 4 and plug that back into the original equation. Okay. Now, this is the easiest of the examples. I'm going to do 3 examples. Okay. This is the easiest one, and the reason it's the easiest one is they gave you the equation. And to be honest with you, in the real world, a doctor or somebody at a hospital is not going to come to you and say, hey, here's the equation. Can you please figure out blah, blah, blah? You're probably going to have to figure out what this equation is. What is the equation that models the behavior of what we're looking at? So let's look at example number 2. This example is a little bit more complicated. Not that the calculus is harder. In fact, the calculus is actually a little bit easier in this one. The problem is look at this problem, and ignore the pictures I've got down here. These are to add to the problem. But look at the words. There's no equation given. You have to come up with the equation, or in this case, equations, plural. says a farmer with 4,000 meters of fencing wants to enclose a rectangular plot that borders a straight portion of a river. If the farmer does not fence along the river, so if this is the plot right here, here's the green grass, if you will, here's the fencing, he does not need to put fencing on that side that goes along the river. The question is, what's the largest amount of area that can be enclosed? And so all I've done here with this picture is I just wanted to kind of show you that, there are parts of rivers that are straight. And we want it to be straight here because this makes the problem much easier for a Calculus 1 student to do. So to start a problem like this, you've got to wrap your head around, how do I get equations out of this? So let's go ahead and look at what we got. We're talking about perimeter, aren't we? This distance around this rectangle. And we know that that amount is 4,000. So let's just say that I made this length here x. So the length from here to here is x, which is kind of that horizontal length. I like to make that x. And of course, I'm going to make this vertical length here. I'm going to make that y. And by the way, if this is indeed a rectangle, then this side is congruent to this side. And then, so that would also be y. So from this picture, I can come up with my first equation. My first equation is going to be 4,000 equals x plus 2y. In other words, I'm saying that this length of fencing plus this length of fencing plus this length of fencing, that's x plus 2y, has to equal the 4,000 meters of fencing. Now there's another equation that we need to write, and I'll do this one in red, because in this question, they're asking us to maximize or find the largest amount of area. And as you guys probably already recall, area is length times width or base times height. So in this case, the area is going to be x times y. Now this gives us two equations, and I'm going to make a note that this one here is actually what we call the secondary equation. And this equation over here is the primary equation. Now, if you have not watched my video that I've already posted on YouTube, you might be thinking, okay, what's he talking about, primary and secondary? You didn't watch the video, you probably should watch the video because I go into more detail about that. So I have my primary equation and then I have my secondary equation. So what we're going to do, I'm going to go ahead and go to the next slide here. And I know that my primary equation, I think I said that that was a equals xy. And then my secondary equation, which I think I said that one was 4,000 equals x plus 2y. So in most of these problems, these optimization problems, what you're going to do is you're going to use the information in the second equation and substitute it into the primary equation. And by the way, the reason, I guess I should say this, the reason that this is the primary equation is because that's what the question is asking us. The question isn't asking us about perimeter. It's asking us about what's the largest area. This is area. We want to maximize the amount of area. We want to have as much area as we can in this rectangle. So what I could do is I could solve this for y. And if I'm not mistaken, I think it's 2,000 minus x divided by 2. So what I've done now is I've taken my secondary equation and I have just minus x over, and then I've divided by 2. So now I've got this equation has now become this equation. And the nice thing about that now is then I can put that in for y. So now my primary equation can be written solely in the variable x, which is x times the quantity 2,000 minus x over 2, which can be further simplified into 2,000x minus x squared over 2. This is what we're going to work with. Now, hopefully you realize that this equation now has only one variable, and it's the variable x, and that variable x is going to represent this length down here. So now we're going to start doing the calculus. And I'm going to find the derivative. And the beautiful thing is this one, the derivative is actually easier than the last one. Using our basic rules for differentiation, you're going to get 2,000. And then the derivative of x squared over 2 turns out to just be x. So a prime of x is equal to 2,000 minus x. Oh, and I guess, you know what, again, I kind of skipped this on the last one too, and I apologize. Let's talk about the domain of this function. If we go back to this problem right here, we know that we have 4,000 meters of fencing. So the absolute longest length that x could be would be 4,000, which would make y equal to 0. So the domain here is 0 less than equal to x less than equal to 4,000. If you remember on our first example that we did, that domain came back to help us and we realized we couldn't have a -4. So our domain here is going to let us know whatever x value we get, it better be between 0 and 4,000. And that's obviously clear here since we're going to set this equal to 0 to figure out that there are a critical number, and there's only one critical number, and it's just x equals 2,000. So the only thing that's going to make our first derivative 0 is 2,000. So if this line represents a prime, the only critical number on it is 2,000. And so let's look at some numbers to the left and to the right. A number, well, if I pick any number less than 2,000 and I subtract, that's going to be positive. If I pick any number to the right, that's going to be negative, which tells us that if we talk about just a, it's increasing on this side, it's decreasing on that side. And so now we can go ahead and draw our conclusion. Therefore, x equals 2,000 is going to give us our max. And by the way, if x is 2,000, we can use this equation here to figure out what y is. So if x is 2,000, this would be 4,000 equals 2,000 plus 2y, and therefore y is 1,000. So y is 1,000. And then the max area is simply these two numbers multiplied together, or if you wanted to, you could plug them into this equation, and you'll get 2 million meters squared. So now, as you can see in this example here, really not hard calculus, but what the challenge was, and this is the part that most students struggled with, in my experience, is figuring out what these equations need to be, because it doesn't tell you what they are. So the secondary and the primary equations, that's the challenge on some of these problems. So these definitely take some practice. The calculus typically isn't terrible, but it's coming up with these values and these equations that's tough. Does anybody have any questions so far? If you do, please feel free to unmute yourself or hit the chat. We're just past halfway, so we just got one more example, and we'll be done. Okay, so I'm going to go ahead and move on. But before I move on, I'm going to give you guys a poll. So if you look, hopefully you will see a poll option. And I'm going to give you just a second to complete that poll before I do my final example. Okay, I'm going to go ahead and start this last example. If you've been paying attention, the poll should be a very easy question. It was based on the last example. So here we go. Let's go ahead and look at example number 3. Now, I'm just going to forewarn you, this last example is the hardest of the 3. So I've saved, if you want to think of it, the best for last. but I like to do a variety of questions simply because sometimes students say, well, Mr. Allen, you just do all the easy ones, and then, the hard ones are on the homework or whatever. So this one's definitely going to be more involved. So I just want to forewarn you of that. The questions 1 and 2 both asked us to maximize. So question 1 was maximizing concentration. Question 2 was maximizing the area. This one we're actually going to try to minimize. We're going to minimize travel time. So it says a small island is 3 kilometers from the nearest point on a straight shoreline of a large lake. A town is 12 kilometers from the shore from the same point on the shoreline. And if a person on an island can row 2.5 kilometers per hour and can walk 4 kilometers per hour, where should the boat be landed so the person arrives in town in the shortest time? Now, guys, obviously this is a very contrived problem. Again, we have, a straight shoreline, which, isn't typical. Somehow people are able to walk at exactly some rate. Again, these are just characteristics that we got to do to make this so that you can actually work this out at the Calculus 1 level. So we're just go ahead and pretend that makes sense. So one of the first things that you can do, and this problem, by the way, is even harder, I think, than the last one, because not only are there no equations given, there's not even a picture given, okay? So what I'm going to do is I'm going to start off by drawing a picture. And I'm going to draw a right triangle. And let me explain why I'm making it a right triangle. This problem says that there's some island, I'm going to call it point I. There's some island that is out in a lake, and then on the shoreline, I'll say there's some point, we'll call it point P, and that distance, the nearest point, which would be this perpendicular distance right here, is going to be 3 kilometers. Then it says a town 12 kilometers from that same point on the shore. So I'm going to call this point over here point T. And I know that this distance right here turns out to be 12 kilometers. So I'm trying to make sense of what this problem is saying. Now here's the thing. The question is basically saying, if I row my rowboat to some point, I'll just mark that point here on the shore between points P and T, and then we would have this distance here. So these two red segments represent the distance that we would travel. Now, please keep in mind, point P is actually not necessarily going to be the fastest way. And the reason is in the boat, you can only travel 2.5 kilometers per hour. You can actually walk in this problem 4 kilometers per hour. So in this scenario, we can actually walk faster than we could paddle the boat. So it actually turns out we can walk faster this direction than we can once we're in the water. So now we got to try to set this up. And what I'm going to do now is in green is I'm going to mark a couple of important lengths. This length right here, from this point here to this point here, I'm going to call that X. And if that's X, then this distance right here would be 12 minus X, because we know the total distance is 12. So this distance here would be 12 minus those X. The other distance we need to know is this red segment right here. This distance is 12 minus X. This distance right here, well, that's the hypotenuse of this right triangle right here. This hypotenuse is for a leg that has 3 kilometers length, and it has another leg of X. So this distance right here is simply going to be the square root of X squared plus 9, which is 3 squared. So what I'm telling you is that the distance, this red distance, is going to be the square root of X squared plus 9. That's this distance. Plus, it's this distance down here, which is this 12 minus X. So this equation represents this red distance, the amount that we're going to go by foot, and then the amount we're going to row by boat. But you'll notice that this question doesn't ask us to minimize the distance. It asks us to minimize the travel time. If we wanted to minimize the distance, you would just take the boat directly from T to I. So we've got to somehow convert this distance formula into something with regard to time. And hopefully you remember that distance is equal to, or actually let me do it this way. Rate is distance divided by time, or I'll say that's d over t. You probably already knew that. So we're interested in time, but we know that, for example, this is a rate, right? This rate is kilometers divided by hours, distance divided by time. So what I can do is I can take this equation, this is r, d divided by t is equal to r, and I can cross multiply, and we will see that t is equal to d divided by r, where d is the distance and r is the rate. This is going to be the key equation that I'm going to draw my final equation that I'm going to use for this problem. Let's do that in red. So I claim that our t function, which is going to be in terms of x, is going to be the distance divided by the rate. Now, this first distance right here, this is the boat in the water. And we can travel at 2.5 kilometers per hour. So I got to do this distance divided by that rate. So that's going to be the square root of x squared plus 9 over 2.5 plus. Now I need to do this distance here divided by its rate. Here's where I'm walking on the land. So now I've got to do this 12 minus x. And then in this case, the person can walk 4 kilometers per hour. So I'm going to divide that by 4. Now, again, I'm going to go ahead and mention the domain right now before I forget, like I did on the last two examples. Our domain here, let me use the correct notation. Our domain is simply going to be 0 less than equal to x less than equal to 12. So as long as x is in between 0 and 12, we're okay. In other words, anywhere in between point P and point T is legal. So this is the key information for this problem. And notice we're already down to one variable. Okay, so now I would like to, I'm going to go to the calculator. And the reason I'm going to do that is the last two problems were very easy to differentiate. This problem is going to be a little bit uglier. If you look at that, you can probably see why. In fact, I would encourage you, if you like to do this kind of stuff, to try to do this manually, and it's actually pretty difficult. So what I'm going to do now is I'm going to go to the next slide. Actually, I'm going to leave this slide up here. I'm going to get my graphing calculator out, and I'm going to turn one of the lights out. I would encourage you, if you have your graphing calculator, to kind of play around with your calculator simultaneously. In fact, you're going to plug this equation right here into the calculator. And the reason I'm asking you to do that is, guys, we are virtual now, and who knows how long we're going to be virtual. So when you take your test next week, obviously you're allowed to use your calculator, but it doesn't do you any good if you don't know how to use your calculator. And this is something I've always tried to do in my classes, but I think it's probably more important than ever is this year making sure students know how to use their calculators. So I'm going to go ahead and do that now. Again, you're going to want to plug this into your calculator. I'm going to turn one light out. Oh, that's not good. Sorry, guys. Sometimes when I switch out of the PowerPoint, it freaks out a little bit. Anyways, hopefully you can see my graphing calculator up here. I'm just using the Wabbit app. I'm actually going to zoom in here a little bit so that I can see it better to hopefully help you guys see it as well. So please just be patient with me here. I want to make sure you can see what I'm doing. Okay, great. That actually looks fairly okay. All right, and guys, please keep in mind, what I'm getting ready to show you, I've actually already posted a video in Canvas under the graphing calculator portion at the very top of how to do this. I'm going to use the derivative graph to find the answer. So if you get confused on what I'm doing here or you can't see, please feel free to watch that video or stick around after class. We got about 10 minutes left and I'll show you how to do that and answer your questions. So I'm going to go into y equals, and I've already typed this equation in. So remember, it's the square root of x squared plus 9 over 2.5, and then plus 12 minus x over 4. And I'm going to adjust my window here, okay? Remember, we've established that the domain was 0 to 12, so I don't need to be less than 0, and I don't need to be more than 12. So I'm going to go, my x min and x max is going to be from 0 to 12. In terms of my x scale, I'll leave that as 1. For y min, I'm not really worried about negative values here because I don't know that that's really going to be too possible, but let's just maybe make that -2. And please, actually, let's do -1 there. I'll explain why I want you to leave that at -1 and not 0 in just a second. And then we'll just leave the y max 10. I'm going to go ahead and graph. So here's our curve of our time function in terms of x. It's kind of interesting, kind of looks parabolic, which makes sense because it has a square root in it. But what I'm going to do now, and this is why I wanted to show you this with the calculator, is I'm going to go to y equals, and this time I'm going to go down to y sub 2, and I'm actually going to graph the derivative of this function. And the way I'm going to do that is I'm going to go to math, and then if you go down to option number 8, you could just click 8 if you wanted. I'm going to scroll all the way down. It says NDERIV. That's numeric derivative, and I'm going to hit enter. So now what it's saying is that the graph of y2 is going to graph the derivative of this. Now it says dd, and I need to put an x there. That's d dx, do the derivative with respect to x. And I could retype this equation, but instead of retyping it, I'm just going to do y1. Now this is the part where students get a little confused, so I'm going to do this slowly. I'm going to go to vars. Then I'm going to go to yvars. Yvars just means y variables. And then I'm going to go into functions by hitting enter, and it says function y1. That's what I want, y1. So instead of having to type this whole thing out, I can just do y1. And finally over here, it's asking me where we want to evaluate this at, and I want to evaluate all the x's in the domain. So I'm going to press X. So what I've done is I have my y1 graph already in there, and now y2 is going to be the derivative of y1. In fact, if I wanted to, I could graph the derivative of the derivative. But I'm just going to do the first derivative, and I'm going to hit graph. So you'll see down here at the bottom, there's a little curve, and it's actually still right around the x-axis, and we can't see it very well. It actually looks pretty bad. So what I'm going to do is this. I'm going to adjust my window one more time here. And this time, instead of going for a y max of 10, I'm going to change the y max to 1, and I'll explain to you why. So it's graphing the, oh, there we go. There's y prime, though. There's the first derivative. Okay, interesting. So you can see here, it was below the x-axis, and here it's above the x-axis. Now, please note, this is what, or in our case, t prime. It's the derivative of the t function. So remember, using the first derivative test, we need to find when the first derivative changes signs from negative to positive if we are looking for a minimum. So let's go ahead and figure out where this crosses the x-axis, and that's what we call a 0. So I'm going to go to second function trace, which is the calculate menu. You probably recall finding zeros in your pre-calc class. So I'm going to find a 0. Now, here's the thing. When you get to this, it says y1 equals blah, 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 blah. I don't want to find the 0 of y1. I want to find the 0 of y2. So I'm going to hit the down arrow, and notice that it changed the equation at the top to numeric derivative of y1. So again, if I hit up, that gives me the y1 graph. I'm going to go down to the y2 graph. And now I got to find, it says left bound question mark. I got to go to the left of where it crosses the x-axis. So I just got to keep hitting my button over here to the left. And I kind of have to do this a little bit more slowly than you might on your calculator because I'm using this thing on the screen. Okay, so I'm a little bit to the left of where it crosses the x-axis. I want to go a little bit to the right. That's what the right bound means. So I'm clearly above now, so I'll hit enter again. It says guess. I'm not going to guess. And I'm going to hit enter. This value right here, and I know it's hard for you guys to see it, but it says 2.4019. That is where the derivative changed sign from negative to positive. Now, I'm going to leave this up here in case you have questions after class, but I'm going to go back now to my presentation. So what I have done now on this example is I just used technology to graph T prime. And it turned out that at 2.40, and I want to make sure I say this right, 19219, over to the left of this, it was negative, and to the right of it, it was positive. So that tells us that for T, it was decreasing here, and now it's increasing there. So that makes this a minimum. In fact, if we wanted to, we could check the endpoints. And our endpoints would be T equals 0, and our other endpoint would be T equals 12, right? Of course, we got this guy here in the middle. But it turns out that, I think I actually wrote that slightly incorrectly. Let me try that again. T of 0 turns out to be 4.2, and T of 12 turns out to be 4.9 roughly. But T of 2.4019, that turns out to be 3.9367. And now we can answer our question. Therefore, and let me make sure I get this straight. It says, where should the boat be landed so the person arrives at the shortest amount of time? So this X value right here, that is this distance right here is our answer, which is this distance here. So the boat should be launched, I'll say 2.402, and I think we are kilometers from P. And by the way, that time, that minimal time, all right, min time is 3.937, and we're talking about hours. So in this particular problem, if I want to minimize the amount of time it takes to get from point T to point I based on these restrictions, the answer is launch the boat roughly 2.4 miles, this distance here, 2.4 miles, and it'll be just under 4 hours when you do that. If you just go straight from point P, it's going to be 4.2 hours. Okay, so that brings us to about a minute left. So the last thing that I'm going to ask you guys to do for me before you're free to go is to answer a exit ticket, which I'm going to post here in just 1 second in the chat. Once you've answered that, you're free to go. If you have questions, you are more than welcome to stay online here, and I will be glad to answer those, but give me 1 second to get this link. And I think let me stop this video as well.